So I went ahead and wrote both of them on there because today is just a lot of trigonometry. Okay, we're going to apply it in different ways, of course, and we're going to use it in different ways, but we're working with trig. So 7.2 in particular is about just called trigonometric So what does this mean? Well, what we're doing with trigonometric integration, what you're going to see when you look at the problems in this section is we don't really have any other function unless you're going to use subs to kind of change it to u and work that out first. But we don't really have any other function besides sines, cosines, tangents, or secants in this section. However, we still run into some trouble because of how they're combining together and what we do with them, right? So, case in point, we're going to start off. I'll just start off with a example here. And we'll kind of determine how to do this on a case-by-case basis. So, the first one I'll present is going to be okay. So I give you this integral, which is just a bunch of trig functions at the moment, but it's the integral of sine squared x times cosine cubed x dx. Okay. Now we know how to do integration by parts now, so I could always say, okay, well, maybe I'll let this thing be my u, let this, be my dv, and then try to work it out from there, right? But notice, really, any combination that we do here, in terms of u's and v's, are just going to be complicated in some way, right? Because I could just integrate a sine or cosine, but then kind of multiplying the other parts together later on down the road isn't probably just going to keep this the same or make it worse. And otherwise, I don't know what sine squared is by itself, and I don't know what cosine cubed is by itself, at least for the moment, right? So we want another way to be able to evaluate this. And here's where maybe we didn't have to do it too much in chapter 6, but really now we need to be keeping in our memory of some of our trig identities, right? The first one that we're going to need is this guy. Now, why would that? Well, let's kind of think about our problem a little bit and kind of see what the powers are we have here. Okay, I have a 2 for the sine and I have a 3 for this cosine. Which, 2, maybe I have a sine, maybe I could replace it and give me all cosines, right? But if I just turn this, rewrote this as cosine somehow, then again, I might get cosine to the 5th power and cosine cubed, which wouldn't really help me. Let's see. How about, right? So what would be really nice, maybe let's talk about a different scenario at the moment. Let's say instead if I had this, okay, so the power still allowed it to be the same thing, but this one's actually significantly easier. Why do we think that is? I could let you sine x, let d go cosine x. So then this is just the integral of u to the 4th. So I get 1/5 u to the 5th, which u is sine, so I would get. So that would be my integral, right? So it would be really nice if I could try to make something similar happen here, right? Well, notice I have cosine cubed, right? And cosine cubed is the same thing as cosine squared times cosine. Correct? Okay. But cosine squared, I can rewrite in terms of sine. Now, why is that going to help me? So let me go ahead and rewrite this equation real fast. Solve for cosine. We're going to get cosine squared x equals 1 minus sine squared x. Right? So maybe I'll erase this real fast just so I can use the space here to complete this problem here. So again, let me reiterate. We're going to have sine squared x, and then we're going to have cosine squared x, and then I have cosine, which doesn't help me at the moment. But maybe I'm going to substitute in for cosine squared. I want to do the 1 minus sine squared. Maybe I'll just, well, actually, let me just go ahead and leave it here right now. Did that, what I just did that help me in any way? What do we think? Is there any trick that I could do to this now to make this work? Good. And maybe I will go slice that farther just in case. So I haven't quite yet. Yes, so now I have this cosine by itself, right? Just as cosine, everything else is sine. So if I let u be sine x here, du is going to be cosine x dx, which takes care of that cosine x dx out there. So now all of those sines are going to become u's. So we're going to get the integral of u squared minus u to the fourth power, right? Sine becomes u, du, right? Because du is cosine x dx. And what's the integral of u squared? And what's the integral of u to the fourth power? C, and then we'll just put a trisecond. So we get our answer. Okay, this is trigonometric integration. Okay, which says, is there some way that I can use identities to manipulate my trig functions so I can properly do some sort of easy substitution to clear everything out, right? Just like here, I said, okay, well, I have 3 cosines, so let me take one and set it on the side, and take 2 of them, and rewrite it in terms of sine, and now I can do a u sub, and kind of sweep, okay? And that will kind of solve all our issues for us, okay? So how's that so far? Any questions there on that? Some of the concept. I'm about to lay out kind of a quick detail, kind of how, if you come to this sort of problem, what steps you take to solve it. But just want to make sure that at least what happened here made sense. Yeah.
Integration by parts would be best. Step here.
No, it will not. I was discussing at the beginning, right? There's what's going to happen is, I mean, there's not really a good pair of sine and cosine that's going to make this work, because especially in each case, right? If I take sine squared, for example, and I take the derivative of that, the power would come down, so I'd get 2 times sine x to the first power, but then I have to multiply by cosine. So yes, I took away a sine, but I also added on a cosine, and the same thing would happen here. So I would still have the same amount of trig functions in a case, and my integral would be just as complicated, if not more complicated. Now, maybe you can do an integration by parts that would get you to like something similar like this, but we don't need to waste our time doing that when we can just do the trig integration instead. Okay. So we're going to start with sine and cosine, of course, and we're going to talk about real quick if I have this combination, right, because a lot of your problems you're going to encounter, right, are going to look something like this, we can kind of think through the different scenarios to see, okay, well, what would be best here? What should I do, right? So the first scenario is, maybe I'll just start with the scenario that was here. If it's odd, take out one. Okay, so case one here is just the case we already went with. Is if my n, right, the power of my cosine is an odd number, then just take one cosine out, right? And then I'm left with an even cosine to some even power, right? But, and maybe I'll just demonstrate, right? If I have cosine to the 6th power x, right? Let's say I took out one cosine and I'm left with 6, okay? The way I can rewrite this in terms of sine is I'm going to take this, and if I take 6 and divide it by 2, what do I get? 3. So I'll rewrite this as cosine squared x to the 3rd power. Right? Does that make sense? You just multiply the powers together. So it's the same thing. But I know how to rewrite this, because that's going to be 1 minus sine squared to the 3rd power. And then if necessary, you can kind of FOIL that out or multiply it out. But that could be after you do the use of, and then it would be. But that's rewriting cosine 6 in terms of sine, right? So that's the idea. Right, so if n is odd, take out one cosine and rewrite everything in terms of sine. And then you can do a use of, and everything clears out easy. Okay, case 2. M is odd. Sine. Everything. Cosine. Okay. So basically the same statement, except instead of the sine and cosine swapped, and instead of n, it's n now. Okay, but this is the same story, right? The derivative of cosine is what? Negative sine, right? So if I take out one sine, I write everything else in terms of cosine, right? Then I just say u is cosine, tu is negative sine. May have the negative sign you have to worry about there, but otherwise it's the same process, right? So you have a u sub, so it's just a polynomial, and integrate from there. It's simple. Okay. Now the question may arise, well, what if they're both odd? Well, fantastic, you have options. You don't have to be stuck to either one, right? This doesn't say if n is odd and m is even, and if m is odd and n is even, right? You can use either one just as long as one of them is odd. Okay, so there's kind of our two basic cases we're going to look for. I'm going to cover what happens if they're both even, or you just have one that's even. But for now, actually, maybe I should mention that real fast. You could also have it right where, I mean, you may only have sine cubed and no cosine, or you may have cosine cubed and no sine, but the same rules still apply, right? You can just take out one and rewrite everything else, right? So maybe I'll just do a quick example like that. Using cosine. Okay. So we'll do example number 2. So we have the integral, and let's see, we want m to be odd, so we'll take the integral of sine cubed x dx. Okay, so let's say I have this integral and it wants me to evaluate it. Okay, so again, if I want to have this, just kind of think of this list here, I see, oh, well, I don't have a cosine, but my m is odd, right? So I'm going to take this and I'm going to rewrite it as sine squared x times sine x dx. Okay, how can I rewrite sine squared in terms of cosine? Thank you. Yep. So I get this, okay? So now how do I evaluate it from here? What should I do? Well, we're going to use u substitution. We don't want to write in terms of sine because that would just take us back to where we were, right? We want to do u substitution. That's why we wrote it in terms of cosine. So u is cosine x, du is going to be negative sine x, which we're just off by a negative sign. So I'll just bring that negative over here. And we're going to get the integral of 1 minus u squared du, and the negative, which you could either keep out here or rewrite it. Maybe I'll write negative 1 minus u squared is the same thing as the integral of u squared minus 1. Okay, and what's the integral of u squared minus 1? I think I'm counting here. 1/3 u cubed. What's the integral of 1? U. C. And just plug in u, which is going to be yes. Where?
That negative.
This one?
Oh, is that negative?
Yeah.
Oh,
Yeah, it's just be a negative sign. Let me make that more clear. Yeah, because it was negative sign, right? But I just said, well, I need that to be positive sign because of here. So let me just bring that negative outside. Negative du is sine x dx. And so that kind of flips around my sign. Okay, so this is the process, right? Really, I mean, it's if you see you have this m or n, kind of the powers be either of them being odd, and just kind of take the steps, rewrite everything. Usually it's going to be a 1 minus sine squared or 1 minus cosine squared you're plugging in. And it's pretty straightforward, nothing too bad there. Okay. However, we have a third situation to worry about, which doesn't really fit as well into this mold, just because kind of the different situations that can arise need to be taken into account, right? So we're going to do example 3 here. We'll talk about the next situation. I'll just do sine squared. Is m or n odd in this case? No, it's not, right? There's no cosine, so the n there is just 0, right? But that's still an even number. And sine squared is even, right? So I can't just take one out, right? If you were to say, oh, well, I'll rewrite that as, sine x times sine x dx. That, I mean, you can't really do a u sub here still. You can't, if you try to rewrite this in terms of cosine, I mean, you can, but you're going to actually make the problem harder, right? If I were to, because sine squared, so you could technically say sine is square root of 1 minus cosine squared, but then you're going to have to work with the integral of 1 minus u squared, which just, we don't know how to do yet, actually, until 7.3. So, I mean, you have that option later today, but not right now. So we're not going to do that. Instead, if we go into the situation where we have these even powers, even if it's just sine squared or just cosine squared, or you have a combination of even sines and cosines, we need to appeal to another formula, which maybe we'll talk about real fast, kind of how we get to it. So, who remembers their double angle identities for sine or cosine? Okay. Just for fun, we don't do that. What is the sine of 2x, anybody? Yeah. So that's the double angle identity for sine, okay? Now cosine 2x here is the one I really want to focus on, and we'll see why here in a second. So cosine 2x, what is that? Good. That's one option. Multiple options, right? That's one of them. There's two other ones, and those are going to be very vital to us. What are the other two options? There is. There's one involved in both. There's one where the one is you're subtracting, and then there's one. You have one minus, and you have minus one. This one is 2 cosine squared x minus 1, and this one is 1 minus 2 sine squared x. Okay, which you would actually get if you just rewrote. You could rewrite cosine squared as 1 minus sine squared, or sine squared as 1 minus cosine. Now, why is this pertinent to us? Well, you mind if I can erase this? This is good. Well, so we know cosine, just for this problem in particular, right? I'll start with cosine 2x. Anything that's 1 minus 2 sine squared x. So notice this is cosine to the first power, right? If I had that inside my integral, I could do that easily because it's just to the first power. I might have to do a u sub, have to worry about that constant on the inside, but it's not that bad, right? And it's equal to 1 minus 2 sine squared x. So what I'm going to do is I'm going to take this expression and solve it for sine squared. Which will give me that sine squared x equals 1 minus cosine 2x. 2. So I can rewrite sine squared in a way that just gives me a trig function of degree 1, which I can integrate easily. Right? And some of you may recognize this if you take the square root of that. That's actually the half angle formula. In some way, you just have to replace the x in here, but it all ties together, right? So that's exactly what I'm going to do. Sine squared is the same thing as 1 minus cosine 2x over 2. And similarly, if we were to solve this one, we would get cosine squared x is equal to 1 plus cosine 2x. So I'm going to rewrite this integral using that sine squared, and I'm going to get 1 minus cosine 2x. 2. It's the same problem. I haven't changed anything. Yes.
Is there a reason that?
It's just happy coincidence. I think that, yeah, that's very true. I think it's very cool. The derivative of cosine squared is also like it's negative sine 2x, but
If you wanted to invert x, could you take sine of 2x and integrate that, and then put it in the integral and integrate that?
that's actually a very good. That's a very good point. You could do that very well. I'll have to think more on that because I actually haven't done that before. We'll stick with the book's method for now to do these, but that's very true. Because it is the same. They're just off by a constant. So we're gonna have 1 minus cosine 2x over 2 dx, right? Just deriving from the sine squared and cosine squared, right? We can make this easier real fast. What can I do with this 2 on the bottom? So I'll just have a 1 half on that side. 1. Okay. What's the integral of 1? Thank you. Make sure after you integrate, the integral sign is gone. There were some that left the integral sign after you integrate. So make sure that's not there. So we're going to have x minus, now when I do cosine 2x, right? So maybe I'll write that on the side real fast. So I'm just going to erase this over here. I'm doing just cosine 2x by itself, right? And maybe I'll just do, instead of doing 2x, maybe I'll just do ax in general. Because I want to make a very similar point to the one that I did with the e to the x yesterday. So if I'm integrating cosine ax dx, right? So just have some constant times x dx. How do I evaluate this integral? What should I do first? Right? Because I know how to integrate cosine x, but I don't know specifically how to integrate cosine ax. So what should I do? We're gonna let u be ax. We're gonna let d du. What's the derivative of ax? Yeah, we get a dx. Okay, which I'll rewrite this as dx is du divided by a, which is going to give us the integral of which I have 1 over a that comes out from du, and we get cosine u du. It's going to be 1 over a times sine u. Sorry, no, it's not 1 over a sine ax. Okay, so notice. Again, you can always use u sub to do that, but if you might encounter this a bit, right? So if you're doing this integral at any time, if you just have cosine of a number times x, just integrate it as normal, right? So the integral of cosine is going to be sine, but then I just have to divide by the number that I was inside the sine, so I get 1/2. Does that make sense? Okay. Again, feel free to you can work it out longer if you need to. I just want to try to provide shortcuts if you can to save you time. We get x minus 1/2 sine 2x plus. And if you were to evaluate that out farther, you would get, or take the derivative, you would get this, but then that's sine squared. So it's an equivalent statement. Okay. Good. So sine squared is that way. Cosine squared, we have 1 plus cosine 2x to do it over 2. If there's a combination, you can replace both of them, right? And then you might have to multiply it out. The things you should still get. The trick is, right? Maybe I'll just show real quick. If you have like sine squared, cosine squared, right? Then you would want to replace both of these, right? Because neither of them are odd. And I'd have 1 minus cosine 2x over 2 and 1 plus cosine 2x over 2 dx, which if I multiply together, I'm going to get 1 minus cosine squared 2x over 4 dx, right? Which I still am left with the cosine squared, but, and maybe I'll just go ahead and take out the 1/4 real fast here so we can see this. I can also rewrite cosine squared again as 1 plus cosine 2x over 2, but now since I have 2x in here, it's going to be 2 times 2x, which is 4x. Okay, so again, I don't want to spend too much time on this, but if you can always replace them as you know, with if they're even, just replace them with that 1 minus or 1 plus cosine 2x, and if you multiply it out and you get another squared or another power, just keep doing it. Keep doing it until you get to just 1, right? They shouldn't give you anything too obnoxious, so you're not dealing with like sine to the 4th and cosine to the 6th, where you have to keep just doing it so many times. But if you do have another one, you can always replace it. Okay, that good? Make sense? Yeah. No. Okay. Great. So that is sine and cosine. That is kind of the sine cosine trig integration side of things. If there is, if there is some sort of like x multiplying with it or something dividing, you might have to do a u sub prior to this or use integration by parts as well. I don't expect you to really have anything that complicated, though. Yeah. Okay. Now let's talk about tangent and secant. So I'll talk about this one, but I just doing an example. So we'll do example 4, and I'll do tangent. Okay, here we go. So, oh, well, this isn't very good. They're both even. So now what am I going to do? I can't do anything with this. I'm just stuck with this expression. I don't know how to, how to fix it now. Well, these both being even actually is not a problem in this case. Okay, let's think about why. We're going to do something similar to what we did for sine and cosine, changing everything. But there's going to be different twists here, right? Because the derivative of sine is cosine, the derivative of cosine is sine. But tangent and secant work a little different. What's the derivative of tangent? Secant squared of x, right? Not just secant, it's secant squared. And the derivative of secant x is secant x tangent x. So notice, I'm not just taking out one thing anymore. I'm going to end up taking out more than one thing. I'm going to take out one secant one. I might take out a secant and a tangent, or I might take out two secants, right? So when we come to these situations, we need to, really think about, okay, what could I do to make this work, right? But still, the underlying thing is, whatever I have, I need to make sure that what thing I take out, whatever's left, I can easily rewrite in terms of just one or the other, right? If I were to take this, for example, and I were to say I have tangent squared, if I just leave one, if I take out one tangent, one secant, for example, there's really not any easy way for me to rewrite tangent in terms of secant or secant in terms of tangent in this case, right? What's our identity that relates tangent squared and secant squared together? Very close. Yeah, you got this slipped. But tangent squared plus 1 is secant squared. So, just like sine and cosine, I would prefer that whatever I had left over to be even powers. So then I can easily, or at least the one I need to change be to even power. So then I can use this formula to, for example, if I just had secant squared here, then I can just rewrite that as tangent squared plus 1. Or if I had tangent squared left over, I can rewrite it as secant squared minus 1. So taking out a secant tangent is not going to be very advantageous for me in this case. So in this case, let's take out a secant squared instead, right? Because that's really my only other option at the moment. You get this, okay? So secant squared is the derivative of tangent, right? So I would ideally want everything that's not that secant squared to be in terms of tangent. So here I have tangent squared, here I have this secant squared. What should I do to the secant squared? Okay, so we get this. Or sorry, forgot about the secant squared. Okay, and in this case, I can say u is tangent, du is going to be secant squared x, which will give us u squared plus 1, du, right? Easily replace everything, and from there, I can multiply it and things will come together. Okay, so very similar process. We just need to be, the powers here we want to watch for are going to be a little bit more interesting. Okay, so any questions on that before I go ahead and kind of lay out the list for this one? Nope. Okay, so again, we're going to label, we're going to have the integral of tangent, the mx, and secant. Okay, so just like last time, we'll start with the case that we did, which is going to be if we're secant, or sorry, we're in is even. If n is an even number, right, then what we'll do is we'll take out secant squared and rewrite everything in terms okay. Now, does it matter what tangent is and what the power of tangent is in this case? And the answer is no, because if tangent's odd or even, it doesn't affect the problem, right? Because you're going to be u subbing for tangent anyway, so the only thing that's changing is the secant, right? So if n is even, then you can just do this case, right? Don't need to worry about weighting this. Okay, second. Let's see. We want m is odd. If you can, and well, actually, maybe let me add a little bit to this. We want n to be odd, and we need n to be greater than because you don't want, you wouldn't want n to be 0, right? Because if m is odd, it doesn't matter if you have tangent cubed. You can't take on the secant tangent to rewrite it. Although in that case, it would be even, so you would just want to use that. I'm gonna check to make sure. I don't want to lead you astray. Straight here from facts. Let's see. So we have power of secant is even, power of tangent is odd. Okay, yeah, I guess it doesn't matter. Okay. So all we need to worry about is n being odd. Then we take out tangent and rewrite everything in terms of secant. Okay, so if m is odd, and assuming you should have some hopefully secant there, you can take it out. Then we want to rewrite everything. We want to take secant x tangent x out, and then write everything else in terms of our secant function. Okay, so then from there you can say u is secant, and so du is going to be secant tangent from there. That will work. So yeah, I think if you want to see, the book does an example of where tangent's odd. If you would like to practice that, to save time, I don't worry about that, but make sure you practice it, think over it. I can't remember which type I put on the homework, but it should be one of the two. For now, I want to kind of get into some of the special cases, okay? Because those are going to be our kind of big guys here we need to worry about. So and this is going to be important because this is going to pop up for a couple of these intervals we're going to do here in a second. So let's see, was that the last one? Except 4, 6, 5. So before we get into some of our more interesting examples here, I want to start off and I want to do the integral of tangent x. Okay, actually maybe I'll do part A here. We'll do because we don't know how to do these, right? We can always integrate sine and cosine, but whenever it came to the trig functions, we had to have, you know, secant tangent, or we had to have secant squared, right, to be able to do them, because that would be secant and tangent respectively. But now we're just doing tangent, now we're just doing secant. So the question is, what do I do? Okay, so we'll get to this one. This one's a little bit not as intuitive, but this one's not actually too bad. So let's think about it. What ideas does anybody have to do this? Right, so I just have tangent right now. Is there anything I could do to that that might help me? Yes. So tangent is the same thing as sine over cosine, right? And then we could use sub, right, in this case, for cosine. Now, let's make sure we understand why it is, right? If I let u equal cosine, right, what's du going to be? Dx. So we're going to get the integral. And now, of course, again, I'll make sure that negative sign comes out, but we're going to get du over u. Ah, what's that? What is the integral of du over u going to be? It's a natural log. Natural log of absolute value of u. C. And u in this case is going to be cosine. So we get this. Okay. Now, this is perfectly acceptable if you do negative natural log of the absolute value of cosine x. It might also be advisable that I can take, right, this negative on the outside is like a -1, right? And if I have a number multiplying outside of my natural log, what can I do with it? Yeah, make it the exponent. So I get cosine to the negative first power. What's cosine to the negative first power? Or same thing, what is it? Secant, right? Because that's the same thing as saying what is 1 over cosine, secant. So this is the same thing as the natural log of secant x. Let's see. Okay, so if you ever want to know what the integral of tangent is, it's natural log of absolute values. Okay, so that would be useful as we continue forward. Let's talk about secant now. Okay, so this one's definitely a lot less intuitive. You might think, but I'll try to make it as intuitive as possible. Okay, so you might think to say, well, 1 over cosine, but that doesn't do anything, right? Because you can't do the same u sub you could here. You're just going to have a cosine at the bottom. You don't know what to do with. So again, let's talk about what the derivative of secant and tangent are. What is the derivative of secant x? Thank you. And what is the derivative of tangent? Okay. Good. So what I'm going to do is I'm going to take this equation we have here. I want to take both these parts and I want to kind of add them together, right? So instead of just the derivative of secant or the derivative of tangent, I'm going to do the derivative of secant and tangent together. The derivative of secant x plus tangent x is going to be, now obviously we can do secant x tangent x plus secant squared x. Since the addition is commutative, I'm going to flip those around. It's the same result, right? Just the derivative of tangent secant squared and the derivative of secant is secant x tangent x. Okay, now why do I bother doing this? What do these two terms have in common? They have a secant, right? Good. So they have a secant x in common. Interesting. So what I'm seeing here is that the derivative of secant x plus tangent x is secant x plus tangent x times secant. Why that's relevant take secant x over 1, and I'm going to multiply it by secant x plus tangent x over secant x plus tangent x. Which is going to give me, right? Because that's just by multiplying by 1, right? Secant x divided by secant x plus tangent x over secant x plus tangent x is 1. I'm not changing the integral, right? But we get this. Now, what did we just say? We said that the derivative of secant x plus tangent x is secant x plus tangent x times secant x. So what we have is we have the derivative over the original function, right? We have, right, if I let u equal to secant x plus tangent x, and I let du be secant x, right, times secant x plus tangent x. That's what the derivative is. Well, then this integral is going to become the integral of du over u. What's the integral of du over u? It's the natural log of u, the absolute value of u, plus c. What's u? Secant x plus tangent x. So this is the integral of the natural log of secant x tangent x. Or sorry, this is the integral of secant x. Is going to be the natural log of the absolute value of secant x plus tangent x plus c. Okay, so not the most intuitive thing to just say, oh, let me multiply both of those, right? Maybe not see it initially, but it does make sense given what the derivatives are, that they both have secant involved. Okay. So I'm sorry, I don't know. I was looking at the book to see what it said, but I think I am going to still make sure to say that it needs to be there. Because then it goes specifically to cover tangent cubed without a secant, and it needs to use something more complicated than this. So I'm going to make an annulment here. This one is a little wrong on that. So let's cover these last couple of examples here, because these are going to be kind of the mark examples in a way we call that that we're going to want to do. So the first here, which we'll call this example 6, maybe you can help with the A and B sort of thing, is we're going to have the integral of cubed x dx, and we're going to have the integral of secant. Okay, so again, I'm doing all this just to make you better at doing integration, right? We all want to improve. We want to kind of be able to, really understand what's going on, really practice around with it, and to make all this work. Okay, so if I were to try to follow the rules here, I can't, just because, n is even, but I can't take out a secant squared because there is no secant squared, and m is odd, right? But I can't take out secant tangent because again, there's no secant, right? So to do this, what we're going to do is I'm going to rewrite this, right? Our ultimate goal is, we said we wanted to derive these to use them somehow in our problem. I'm going to take this and I'm going to rewrite it as the integral of tangent x squared x dx. Okay. Now, the reason I'm doing that, right, is I couldn't get anything at the moment. So the idea is maybe I can involve secant somehow. Maybe I can get secant involved to do something with that. Okay. So what I do is we have next to do this. So I said, I did that, you know, maybe we'll take that 3 and write it as 1 and 2. What can I do with this tangent squared, actually? Yeah, so tangent squared, right? Here, right? We would take tangent, rewrite it as, oh wait, yeah, no, we take secant squared of some form and rewrite it as tangent squared plus 1. But here, I'm going to take tangent and I'm going to write it as secant squared minus 1. Okay, now why do I do that? Well, let's see if it helps us. So we're left with this. Okay, so I have secant squared tangent minus tangent, and I want to integrate this thing, right? Do I know the integral of this? Yes, we do. We have it. Okay, so now let's just focus on, can we do the integral of this guy? What do we think? Can we do this? Yeah, we could do actually, yeah, there's the both options are here, right? Because this kind of turned into this situation now, right? We have n is even, so I could just do secant squared and let u be tangent, or m is odd, right? We have tangent to the first power, right? So I could take out a secant tangent and then let u be secant. We really have options here. It doesn't matter. So maybe let's see. We haven't really got to use the second one yet, so we'll take out a secant tangent, right? So but either way works fine. So we're gonna rewrite this as secant tangent, secant, and then minus tangent x, right? Now it says to rewrite everything in terms of secant, but the only thing we have left here is a secant, so I don't have to worry about it, right? Maybe let me go ahead. Integral of tangents what? What is the integral of tangent? So you know I just need to worry about this part. So how do I evaluate this? So we'll let u be what? Secant, good. U to be secant x tangent x. Yes. Which is going to give us, here at least, we're going to get u du, right? Because we have u, and this part's du. And what's the integral of u? That, at least this part, is 1/2 u squared plus c, and we'll plug the u in. So all in all, I'll write the final answer over here. This is going to be equal to, right? So we get 1/2 u squared from here, and u is what? What is u? Secant. Yep. So we get 1/2 secant squared x, which again, if you wanted to do, if you had tangent instead, that's okay, because you really could do these other way. I could let u be tangent, and then the u would be secant squared. That's okay. It's the same answer, except maybe I'll apply a constant. But we're not. Actually, I wonder. I think the book. I wonder if the book does. Yeah, the book has tangent instead of secant. But, so both are balanced, but I'll do secant for now. Just we'll keep things mixed up here. Okay. Minus the natural log of the absolute value of secant. So that's your okay. So I would really think about examples like these as you're practicing and working through these sorts of problems, right? Because here, this was still kind of fell into this group, but because we had this extra minus tangent here, we had to know what the integral of tangent was. Okay, so let's do this one, and then we'll call it, basically call it good there. So what ideas do we have for this one? Try the same thing? Yeah, absolutely. So I'm going to rewrite the integral of secant squared x times secant x. Now what? anywhere. What do I do now? Okay. We're going to rewrite secant squared as tangent squared plus 1 dx, where we will proceed to get the integral of squared x times secant plus secant. Okay, so again, we know how to do the integral of secant, so we already did that over there, so we'll leave that guy for now. For now, we need to figure out how to do tangent squared x times secant. Okay, so let's see. Do we have n being even? No. Do we have n being odd? No. So this is kind of another special scenario we're going to have to think through, right? In this case, no. Okay. So again, you know what this guy is, so we'll come back to that. We need to figure out what's going to happen here, right? So maybe I want to make some room so we can do this. Okay, so let's see. Trying to see if I can still salvage my rewriting that as tangent squared plus 1 way. I think I might do that. It could probably work in some way, but maybe I'll stick with the book's boring way to do this. So I'm sorry. This here we will. If you want to try this, please do. I'd be interested to see. You know, obviously you can still do this, but what tricks you might use to do that? You could probably. Yeah, you could probably do it by parts, and that's actually what I'm going to do here. It's going to be a little bit easier for that though than it would be here, because, and we'll see why, right? Because I don't know what the integral of tangent squared is, but I do know what the integral of secant squared is. So that's going to really give me be the vessel.
I've been integrating by parts with secant x, tangent x.
Oh, I see. Oh, that would work too.
You know what the derivative
Secant x tangent x is, right? Yeah, that's true. Well, let's do it that way then. Why not? Sorry. I like to try to make this as fun as possible. So we want to keep things interesting, right? We don't want to do everything the same. This okay. So the book again says to just keep the secant squared and secant x, and then it works on doing an integration by parts, right? Because at this point, right, again, why do we even have to do that? It's because we failed both of our conditions, right? In the secant squared and secant case, or in the secant cube case, we have an even m, we have an odd n, so both fail. And in this case, I have an odd n and an even m, right? So this fails also, right? But what we're going to do, this guy is good. We'll just kind of cut him off for now. He can join the party later. We're going to focus on this at the moment. So I'm going to rewrite this as tangent times secant x, tangent x. And we'll have this, okay? So now the idea here, right, that the book does and that we're going to do here as well is that we want to use integration by parts again. So we're going to kind of bring that back in and work it out this way. So why integration by parts? Well, we notice that we have secant x, tangent x, right? We had one secant and one tangent here, which is easy to integrate. And I have a tangent, which is easy to take the derivative of, right? I mean, secant x, tangent x, I guess isn't that hard to take the derivative of, but it would give me a lot bigger kind of grosser expression. So we're gonna do integration by parts. Maybe I'll write IVP so we can know what's going on, right? So I want to let U be tan x. We're gonna let du dv be secant x tangent x. Yes. So what is du gonna be? Secant squared. Thank you. And we're gonna let b be what? What's b? Secant x. Good. Because that's secant x tangent x. Okay, so we just get secant x. Okay, so then using my formula, I'm going to get I'm going to get u times v. So we're going to have tangent x times secant x minus the integral, right? So let me write the integration parts again, just in case you forgot at this point. Secant x tangent x minus the integral of v secant x times du, which is secant squared x. And so we're left with this. Okay. This is a little bit of a problem, right? Because this is definitely not what we want. Right? Because we still. Right, that's the original thing, right? So this is, but remember yesterday we did this e to the x and sine thing, so maybe we can do something similar here. So this is, so let's recall everything, right? So I was just doing this portion, right? What is the integral of secant x? Yes, thank you. So, and we just did some integration by parts on this part, which ended up giving us the expression we already had, right? Which is secant cubed, right? So I'm going to write everything out pretty big here. So we were wanting to find the integral of secant cubed x. We had, so this part we found was secant x tangent x minus the integral of secant cubed x, right? And then plus the integral of this part, which is the natural log of secant x plus tangent x. And then you have plus c over here, or which you can worry about later. Okay, so we're left with this, right? So I have the integral of secant cubed x, which maybe from yesterday I'll call this I, is going to be secant x tangent x minus I, plus the natural log of secant x plus tangent x plus c. So what should I do? What do we think? If I want to solve for secant cubed x. Add it to both sides, thank you. So I'm going to get 2i secant x the natural log of secant x x. Okay, and then how do I solve for I? Divide by 2. Bear with me here. Probably not. I is going to be secant x tangent x plus the natural log of secant x plus tangent x all over 2, and then I'm just going to put plus 2. And that is okay. So a bit of work really just requires us to think, right? And I think this is one of the sections that can both be easy and be difficult, just because you really need to be, you have a lot of scenarios to think about, right? But don't get too overwhelmed by it. So the nice thing is I just did the integral of tangent cubed and secant cubed here, right? So if you're working on a problem and you pop up with a secant cube somewhere, you can say, oh, we did that already, right? You can argue by he did it in class, so I don't have to do it. You want to practice it, please, by any means, but we want to create these building blocks, right? So we can work from there, build back. We'll go ahead and take a break for now, so you can go ahead and do what you need to. There's like some last formulas here. I'll write them if you want them, but I don't need to really discuss them too in depth. But so for the rest of everybody else, just feel free to go on break for now. We'll take 10 minutes and start again at 4 or 4:07. Let me get these on here. So just you encounter this situation. You can also just take a break. If you're given a problem that you have a combination like this, then you can use these for writing